We'd also like to thank our Compugen partners, Inbal, Tal, who's joined us, and Nimrod, as well as our wide data mentor, Shani. So what is Compugen? Compugen is a company that uses machine learning and data science for oncology problems, to cure cancer. And that's what we came here to do as well. Our goal was to try and help in the war on cancer. And so what were we studying? We were studying things called TLS structures, Tertiary Lymphoid Structures. What are these? These are clusters of immune cells that form near a tumor, and they sort of function as advanced outposts of the immune system when it's fighting the cancerous growth, when it's fighting the tumor. Now, why does TLS classification matter? Why does it matter if we know whether there are TLS structures or not? Well, the presence of TLS structures is a very positive indication on the functioning of the immune system. And if we see that there are TLS clusters in a patient that has cancer, we're more likely to recommend various immunotherapies rather than, if we don't see them, we'll have to recommend much more aggressive therapies to treat the cancer. So we can see that TLS classification really deals directly with curing cancer, helping cancer patients. Now I want to talk a bit about our data when it comes to TLS classification. A patient has cancer. Specifically in our case, we dealt with patients with colon cancer. The cancer is biopsied. You cut part of the cancer off, and then you slice a very thin slice from the part that you cut off, to the extent that it's to the depth of one cell. And then you scan this slice, and you get a slide, such that you have hundreds of thousands of cells in each slide. For each cell becomes a row in our data sheet, in our spreadsheet at the end of the day. So the rows are cells, and the columns are genes. So cells have genetic material in them, and each gene is expressed differently in each cell. And the value for each cell, for each gene, is how much that gene is expressed. It's the gene expression for the particular gene, for the particular cell. That's most of the columns. That's about 960 columns. And then we have 2 extra columns for each cell, which are X and Y coordinates, where the cell is located spatially in the slice. So our project is 2 tiers. Tier 1, both tiers involve classifying TLS structures. Whether we want to know whether a cell is a TLS cell or not. The difference between the 2 tiers is that in one tier we're allowed to use the spatial data, and in the second tier we're not allowed to use the spatial data. And there's a reason for this. There's a lot of disassociated data which is available online for free or very, very cheaply. So if we're able to solve the problem that is disassociated without the spatial data, Compugen will be able to download reams of data from the internet and work with that data and develop future products. So what was the data set we had? So as I mentioned, we have these slides. So we have 14 different slides cut from different patients, different hospitals. Each slide has hundreds of thousands of cells. Those are the rows, roughly 960 genes. Those are the columns. And then the label is whether each cell is a TLS cell or not. This labeling was done by Inbal, the great biologist at Compugen. And she does this by hand, looking at the gene expression, looking at the slide. You can imagine this is a very, very difficult task to do. There's hundreds of thousands of cells. And so what she does is she sort of draws a border around the TLS structures. And she draws this by hand. And so when she's drawing it, there can be some kind of a mistake that she makes slightly. But there's a more fundamental problem when it comes to the labeling, which is that ultimately we're asking a question whether a cell is a TLS cell, yes or no, 0 or 1, complete binary. Whereas in biology, things are a bit more complicated. If we look at a cell now that isn't a TLS cell, over time it might become a TLS cell. If we biopsied the same cancer 6 months later, maybe this cell would have been a TLS cell. And so there's a more fundamental problem with the labeling, which is that there's a biological fundamental uncertainty. Here's an example of a slide. You can see in red, those are the TLS structures. In green, those are the epithelial cells, which usually means the tumor. And you can see that these TLS structures form outside the tumor. It's sort of an advanced outpost, but not quite inside the tumor itself. And one of the things you can see in the slide is that it's very imbalanced. The vast majority of the cells, in this case, a ratio of 25 to 1, are not TLS cells. Overall, in the whole data set, it was 27 to 1. This creates a challenge for us. If we use a classifier that's too simple or we don't take into account the minority class, it's just going to guess that everything's not a TLS cell and get very low loss. So we need to take this into account. One of the ways we took this into account is you'll see later in the results slide, we got rid of a lot of we also use class weights, we use many things, but one of the things we did is we got rid of a lot of the data that was not TLS data. In the tier that was spatial, we obviously kept more of the spatial context. In the tier that was not spatial, we didn't. But we really have like many millions of cells, and so we felt comfortable focusing on the TLS cells that we had. And the other thing you can notice is that the TLS structures have a very particular geometric form. They're clustered together. Cells that are TLS are next to each other, cells that are not TLS are next to each other. This will be an important consideration when Maor tells you about model selection.
Thank you, Alex. So we've been working with three foundation models. We have scGPT, scGPT Spatial, and Nicheformer. So the first model, scGPT, uses, so if we take simple LLM that we all know and love, LLM that works with words and sentences. So we look at the architecture behind ChatGPT. So we go over all the internet, we take one sentence, then the model needs to predict a single word from the sentence that we hide, that we mask. And this way the model learns the English language, for example, or the coding language, Hebrew. In these foundation models, we're working with biological LLMs. So here the data is not words, it's cells. So we take a cell, inside the cell, like Alex said, we have gene expressions. Now we mask gene, we hide gene, and the model needs to predict which gene we hid, we masked, and this way the model learns the biological language, actually the cell's language, which is quite remarkable. And in these two extra models, so here we use spatial context as well. So we don't only predict genes from each cell, we consider the neighboring cells of each cell, and this way the prediction gives the model actual spatially aware embeddings, and the model can connect not only the genes inside the cells, but the neighboring cells inside the tissue. So these are the foundation models. And the two tiers, so Alex explained briefly, in tier one, so we use spatial context. We start with the data Alex showed you, and then we pass the data through scGPT, and we get embedding for each cell. And then we put GNN, we connect GNN on top of the embedding we have. This way we refine the embedding, and we put classifying on top, TLS classifier, yes or no, it's a binary classification. And in tier two, so it's an end-to-end fine-tune. So again, same data, slightly different because we take different upsampling, but basically the same. And we put the model, the scGPT, for example, model, and we have decoder on top, and the model weights get updated with the decoder, and we get an end-to-end fine-tune. So this is it. And the baseline for both models is we take frozen weights, put classifier on top, and that's it. So regarding GNN, graph neural network in tier one. So we start with H1, which is the original embedding of the cell. All these H's around him are the neighboring cells, and we get a weighted average of the neighboring cells and get a new embedding, H tag 1. This is the new embedding we get from the GNN. It's an embedding that is more spatially aware, and it's connected to the TLS classification, which is what we're interested in. So this is how we get in tier one. Okay, so let's get to the results. So our evaluation metrics, we have ROC-AUC and PRAUC. ROC-AUC is for overall assessment of the model. PRAUC for focusing more on the positive class, the minority class, because we have recall and not false positive rate in the x-axis. Okay, so for tier one, first of all, the three first rows do not use spatial information. They do not use the spatial coordinates. We simply take the data like tables and we just predict. And what was pretty surprising to us that the fine-tuned scGPT and scGPT spatial outperformed the models that used spatial coordinates, but we'll say that the spatial coordinates improved the model, the baseline results by a large margin, 33, 32%. These are two different types of graph neural networks. One uses convolution, one uses attention. So we can see large improvement, and we can actually plot it on the slide because we have the slide, we have the actual predictions. So let's see it. So this is GATT. GATT is graph attention network. It's one of our GNNs. And we can see that we have clusters of false positive, island of false positive. False positive is in red, and true positive are in green. We can see that we have majority in neighboring cells, like we expect from GNN models. We can see we have a lot of islands here of false positives, but like Alex said, it might mean that maybe they're immune cells that might become TLS, or the model just makes mistakes, but we need to investigate it. But this is what we would expect from a GNN model. So this is it. And if we look at the other model, let's take, for example, scGPT spatial fine-tune. So because the model predicts row-wise and not based on graphs. So So the false positives, the reds, are disorganized. We have more sparse mistakes, but we do have more false positives in the boundaries of the TLS clusters, if you can see. So we can actually use both models. We can make, for example, an ensemble of both models to get the best of both worlds. And this is regarding tier 1. And indeed, we got much better result than the baseline, and our baseline is a very good baseline. It's a scGPT biological LLM model with frozen weights that we use to classify. So it's major improvement. Now regarding tier 2, again, tier 2, we don't have spatial coordinates. We regard it as data, disassociated data, as table. So here we used, So here we can see that we have Nicheformer as well. scGPT spatial and scGPT outperform Nicheformer, and as we expect, scGPT spatial got the better results in tier 1 and in tier 2 as well. So the test here is ensemble. After we did an ensemble of all the 6 folds, we tested on a holdout test and got these results. And when we look again at the slide itself, so we can see here that most of our false positive are in the borders of TLS clusters and are more closer to the TLS clusters. So we've investigated it, and yeah, we got to some really nice insights. We don't have it here, but yeah. Okay, so this is it. And if we look at scGPT, this is fine-tuned scGPT. Pretty similar result. We have slightly more here false positive. You don't really see it too much, but that's it. Now, using TLS classification, we can identify important genes, important cells. We can actually dive to attention maps and actually look which genes are more important and what's the relationship between the cells. And we can get to better cancer treatment, better medicine development, and by help a lot of cancer patients. So, thank you. This is Yuval from Nepal.